GRASS is an open-source GIS system that's supported by thousands of developers. In this presentation from O'Reilly's Where2.0 conference, UC Davis graduate student DylanBaudette discusses all the technical details of GRASS and even shows how it can be used to plan a wilderness hiking adventure. From IT Conversations.
Okay, yeah, I'd like to thank everyone for, especially O'Reilly and whatnot, for having me here. I'm not actually a GIS specialist or anything like that. I just happen to use GRASS in my work. I'm a soil scientist at the University of California, Davis. And I was given the opportunity to come speak here by two of the lead developers, Marcus Nteller and Helena Minasova. I'm going to give a little background on kind of a case study approach to using GRASS for planning a wilderness adventure, something many of us probably can relate to. Okay, so I'm just going to quickly go over some of the history on GRASS, some of the data types, just to get some of the vocabulary in our minds while we talk about this stuff. The component model of how GRASS works, how it interfaces with other software, relational database systems and statistics packages and whatnot. And then finally I'm going to jump into the analytical example here of planning a wilderness adventure. So, brief introduction, GRASS was developed in 1984. It was a public project by the US government. And since 1999, it's been open source and actively developed by a team of developers all over the world, with the efforts focused in Trento, Italy, under the direction of Marcus Nteller. Obviously, it's open source. It's multi-platform. We've got Linux, macOS, Windows. People have even ported it to iPacs. Anything that can compile ANSI can run GRASS. So what does it do? It can deal with two-dimensional and three-dimensional vector data. We're all familiar with points, lines, and polygons. GRASS can take that a step further to deal with faces of three-dimensional volumes. They're centroids. Three-dimensional raster data, so voxels, the three-dimensional representation of pixel data that we've been accustomed to using. Some of these supported data types, again, with some nice pictures. We're familiar with seeing orthophotography and Landsat data presented as a backdrop behind Google Maps. While it's nice to be able to see how our route from our house to Grandma's house relates to that satellite data, GRASS actually allows you to interact with that data and calculate new data that you can use either for personal interest or scientific exploration. Lots and lots of possibilities. A quick overview of what a raster data model is. The idea is you have a data set where you represent some natural phenomena with a matrix of values on a regular grid with some sort of inherent spacing. A lot of times that spacing is referred to as a grid resolution. Some common examples of this, again, any kind of imagery, that's raster data. Digital elevation model, instead of having color encodings at each cell, it'll have an elevation at each cell. So this is one of the main data types that we'd be working with in a GRASS system. And again, the vector data, points, lines, polygons, and as I mentioned earlier, areas, faces, kernels, volumes. These are concepts that don't necessarily exist in many of the other GIS products. And they're currently undergoing rapid development integration right now in GRASS. So how does GRASS fit into the bigger picture? With its Unix background, some of the closest neighbors it has in this kind of component model, bash scripting in the Unix toolbox. So essentially when you work with GRASS, you have all of the Unix text processing tools and data manipulation tools like set and awk and grep and using pipes to move data around. You know, that's certainly possible and allows you to do a lot of interesting analysis very quickly. But for more complicated stuff, you can hook up a database engine, MySQL, Postgres. There's about 7 or 8 different drivers out there. And there's also a framework for directly moving GRASS vector and raster data directly into the R project, which is a very mature data analysis program. Normally it's used for statistical analysis, but some recent articles in the GRASS newsletter have been contributed dealing with fixing up errors, systematic errors in Landsat data using R, and then moving that back into GRASS to have a higher quality or kind of a value-added version of Landsat. So this is the kind of the stuff that you can do with this kind of fully functional, mature GIS system. And underneath the import and export framework in GRASS is the GDAL OGR libraries, which allow GRASS to interoperate with all of the relevant geographic data sources out there. Okay, so now for the exciting part, this sample application. What we're going to do is we're going to go find some topo maps and some elevation models on one of the many servers out there. The Seamless USGS server is a good one. If you're in California, the California Spatial Data Library, CASL, is another great source of these things. These are all public information, and so we all have access to these without any kind of cost. And people have designed interfaces to rapidly find and download these sets of data. So we're all familiar with topo maps, or probably familiar with the printed variant of these. Again, a digital elevation model, again, it's just a grid. Each cell represents an elevation. So using these two sets of data, we want to plan a wilderness adventure here that deviates from the main trail here in the Kaiser Wilderness, just east of Fresno, California. So we're going to go visit some of these lakes. Before we do that, we have to get the data into GRASS. So this is a good time to talk about the import and export tools, just the import first. Before that, this kind of central region here is talking about describing how the GRASS data storage metaphor that's used. There is a database, a location, and a map set. A location defines a set of map sets that are all within a consistent geographic coordinate system, or any type of coordinate system, a consistent coordinate system. And a database houses many different locations. So in many ways, if anyone's familiar with some of the Esri products, the concept of a workspace and a coverage and things like that, there's some overlap there. And there's various tools here, v.in.ogr for importing any type of vector data, raster data, ASCII data, if you happen to have a CSV file of latitude, longitude, and whatnot. Ways to get in data from a GPS or a WMS service off the internet. So here we are. Here's the topo map, and this is just a simple operation to kind of drape it over a hillshade. This is pretty standard in GIS analysis. It helps you visualize the topography. And what we're going to do is, again, we're going to deviate from this main trail here and visit these lakes. So I'm going to speed up a little bit. First thing we want to do is we want vector representations of the trail features and of our points of interest. So these trails are the dash lines. So you can use the v.digit command to on-screen digitize these lines. It took about 30 minutes for me to do about a quarter of the topo sheet. It's not too bad. And then pick out the points of interest, these lakes here. So those are now converted into vector lines and points, which allow us to do analysis on them. They're no longer pixels inside of a raster map. The next thing we want to do is, well, I want to know where these lakes are and where the wooded areas are. And this is some kind of complicated looking garbage here, but what this is this is a series of commands that you can use in GRASS to essentially reclassify this topo map to pick out the wooded areas and the lakes and clean them up a little. So r.reclass here allows me to say, okay, I want features coded as woodlands and coded as lakes, make those into a new map. r.grow will kind of allow each pixel to grow out, filling into its neighbors, so I can clean up some of the artifacts from the original map. They're a little bit hard to see, but there's kind of bands in here where the contours were. That allows us to expand out these features, kind of fill them in a little bit. And then r.reclass.area is an example of a command that can take this raster data and throw away features smaller than a given size. So what I did is I threw away these lakes smaller than 0.3 hectares. So what I end up with is a nice, clean, albeit raster representation of wooded areas and lakes. And why I did this will be apparent in just a second. So we start with our elevation model. And if we want to build a model for going off of a trail, we need some measure of choosing that path. What is the best way to get there? What is this least cost approach? This is a pretty straightforward GIS application that's in many different packages out there. Just one quick example. So before you can calculate this least cost, you need some concept of friction. In this case, I'm using a slope map, which is computed from the DEM. And then thinking to myself, I don't want to go through lakes, so I'm going to give these lakes, and I'll explain this in just a second, I'm going to give those an arbitrarily large number. I'm going to add that to the slope map such that when I compute this least cost path, that I'm not going to be going through lakes. So kind of how it works, the tool r.cost will use a friction map, a starting point and a stop point, and it will add up the cumulative cost, in this case slope, kind kind of from the idea that traversing large slope gradients is uncomfortable and painful, and when we don't want to be doing that. So what I've done is use this r.cost from one lake, in this case Bill Lake to Bonnie Lake, as an input, and using the friction map, the slope map that has the lakes given a large value at their point and the wooded areas given a slightly lower value at their locations, so that we can trace out, or have an algorithm trace out, this least cost path. This is kind of a representation of it on a cost surface. Mind you, this isn't necessarily elevation here. This is kind of the amount of effort it takes to get from one place to another. I'm going to quickly go through these last slides here. Doing that for all the different points, all the different lakes, this gives us then a network of least cost paths between all of our points of interest. Converting those into vectors with some of the vector tools, v.patch, and using this command d.path computes an indice of network connectivity, which helps us locate where some of these vectors don't quite line up. Again, we can use that on-screen digitization tool, v.digit, to clean up these vertices, snap them together, and recreate our topologically correct network by having vertices that match at nodes and whatnot. And then we can do some interesting network analysis using v.net.path, for example. We could do a traveling salesman problem of what's the best way to get from each of these lakes in the shortest amount of distance and whatnot. Here I've just shown the fastest way from this point to this point, and it's highlighted in red. Again, one of the many different things you can do with this analysis. Looking at the output in 2 dimensions with QGIS, one way of interfacing with GRASS data. Looking at it in 3 dimensions with InViz, which is bundled. It's part of GRASS. It's kind of an interactive 3D viewer. And then making a printed map with the generic mapping tools. This is just one such example. And if anyone's curious, I've posted all this information up on a website with all the code and whatnot, so I'd be happy to share that. Again, further things you could do, you could figure out the position of the sun at any certain time of the day. When is a good time to take pictures of Kaiser Peak? When and where will I be hiking in the shade? Things like that are all possible with the analytical capabilities in GRASS. Again, here's another example. So really, you're only limited to your own creativity with a tool like this. So that about wraps it up. Thanks.
You've been listening to a presentation from the O'Reilly Media Where 2.0 conference.
The post-production audio engineer for this program was Jeremy Glenn. Our website editor was Sathyesh Chakravarthi. The series producer is Kevin Shockey.
This is Phil Windley. I hope you'll join me next time for another great presentation from the O'Reilly Media Where 2.0 conference here on IT Conversations.